All right, here we go. When people ask how I take images of things like Saturn and Jupiter, sometimes it's hard for me to concisely explain it. There's a lot that goes into it, and even some of the easier ways can still be difficult. So, I'm going to go over my process for planetary imaging, which in the astrophotography world we call lucky imaging. This is in contrast to deep sky imaging and wide field imaging, which both use very different techniques. I'll explain what lucky imaging means later, but first I'm going to start with the very simplest part of my process, the gear. Alright, so this is the setup that I'm currently using as of fall 2023 for planetary imaging. I'm going to start from the bottom up. Right here we have the mount. This is the Ioptron GEM 45. It's an equatorial mount with a 45-pound payload capacity. This is a tracking mount, which isn't actually necessary for planetary imaging, but it is helpful, as I will show later. And this is a really precise tracking mount as well. This is also what I use for deep sky imaging, which requires precise tracking, so I use that for that as well, but I'm usually using a different telescope for that. But anyway, on the mount is, of course, the telescope. This is the Celestron C9¼ Schmidt-Cassegrain design. So the Schmidt-Cassegrain design has this corrector plate here. There's a primary mirror in the back and a secondary mirror up here, and thus making it a much shorter tube for a really long focal length. So we really need a lot of aperture for planetary imaging to get some of those finer details on the likes of things like Saturn and Jupiter. So really most planetary imagers are starting at least 8 inches. And this particular design of telescope makes it really convenient to put on a mount like this. I do also have an 8-inch reflecting telescope that's really big. It's pretty tall, stands about 4 feet when it's standing straight up. So this is a much more convenient design, which is great for planetary imaging. On the back here, I'll flip around the telescope so you can see the camera. So attached to the telescope is the camera. That's this red apparatus here. This is the ZWO ASI 178MC. This is a planetary camera. So what that means is it's pretty small in comparison to some of the other astronomy cameras out there. It's got a really small chip because we don't really need a big chip to fit the planets on said chip because the planets are so small visually. And it shoots at super high speeds. So it's got a USB 3.0 here. It's got to be controlled with a laptop or a computer because it has no buttons on it, obviously. And also it takes a ton of data at, again, a really high frame rate, which doesn't really work with most conventional cameras. So like I said, it's got to be plugged into a computer of some sort. So that's the whole setup. Plus there's a couple other small things that I have lying around here that I usually use while I'm recording, like cables and stuff like that. Total, this would run you, the mount itself, new, is about $2,500. The telescope is $1,500, and the planetary camera on the back is $250. I got the mount used, so I saved a bit of money on that. All said and done, I paid probably about $3,500 for this whole rig. So quite a bit of money, but at least to me, it was worth it. So not unlike other types of photography, some planning and preliminary knowledge are key to successful imaging. Let's start with the things I don't have control over that need to be understood in order to get good images: the weather and the location. Technically, there is some control to the location, but I generally shoot from my home in the city for planetary, and I'll explain why later. Clear skies are obviously a requirement for any kind of astrophotography, but astrophotography is much more demanding of the weather than simply a clear night. No matter how good your gear is, the most important weather factor for planetary imaging is called astronomical seeing. Astronomical seeing, or just seeing in this context, is how much the atmosphere distorts the view of space. This is mostly determined by wind speeds in various layers of the atmosphere, but it can also be affected by things such as nearby heat plumes from city buildings. Astronomical seeing can be forecasted, but forecasting astronomical seeing is wildly inaccurate compared to normal weather forecasts due to the volatile nature of atmospheric winds. Unlike deep sky astrophotography, light pollution and nearby streetlights are not actually a problem for planetary imaging since the planets themselves are particularly bright. As long as you can see the planet, light pollution doesn't really affect images. This is why I usually shoot from home for planetary imaging. Smoke and dust, usually from wildfires, are also not generally an issue, but can be if they are bad enough. Another factor we have no control over is the location of the planets themselves. As we orbit around the sun, our view of the planets changes based on where those planets are in relation to the Earth and the sun. While the planets are generally always viewable at least some point in the night, sometimes they are too close to the sun from our point of view to be viewable, or only viewable for very briefly near the horizon around sunrise or sunset. However, approximately once a year, each planet moves into opposition, which is when we are closest to the planet in our respective orbits. Intuitively, this is when a planet is the largest and brightest in the night sky. So ideally, you want to image the planet when it is at or near its opposition. This is also affected by your location. The higher your latitude, the lower they will be in the sky, which means the more atmosphere between your telescope and the planet, which again means more atmospheric distortion. All that said, unfortunately, good astronomical seeing is rare here in North Carolina, and poor astronomical seeing makes detailed images of the planets impossible. The jet stream, which destroys astronomical seeing with its super high wind speeds, frequently moves over North Carolina, ruining the possibility of high-resolution planetary imaging. During the winter especially, it is basically parked over North Carolina as it's pushed farther south by the season. Fortunately for this year, the opposition of Jupiter and Saturn occur in late summer and late fall, which is usually when jet stream interference is a bit less common. This means we might occasionally get the opportunity for ideal shooting conditions, and thus preparation for such events is absolutely critical. Expert astrophotography requires patience on the scale of months and possibly even years. Depending on how good the seeing forecast is, I will usually just check with my own eyes before going out. I can usually just simply tell by looking at how bad the stars are twinkling, but if I already have the scope out, I'll just simply look at the planet and see how steady the view is. If the view looks good, I'll attach the camera and start the imaging process. So now on to what we must do in order to take advantage of these rare opportunities of clear skies and good astronomical seeing. This part of the process is entirely on me, and it's important to get the things right if I want a good image. The next most important factor in planetary imaging behind astronomical seeing is collimation. Collimation is the alignment of the optical elements in your telescope, and since we are hoping to get the smallest possible details achievable with our telescope, collimation must be perfect or near perfect for best results. The process to collimate a telescope depends on a bit what kind of telescope you have, but for me, I use the 3 screws on the front of my telescope to adjust the alignment of the secondary mirror. These are actually upgraded screws called Bob's knobs. They allow me to adjust the screws with just my fingers instead of a screwdriver, which is hard to use in the dark. They are a cheap modification that most planetary imagers use because collimation must be checked before every imaging session. If you have a refractor telescope, they do not generally need to be collimated, but consumer-grade refractors usually do not exceed 6 inches, which means they are not ideal for planetary imaging because, as I said earlier, you really need at least 8 inches to really resolve some of the details that you'd want to see. After I set up and check collimation on a nearby star, I can finally get focus and start shooting. Unlike in deep sky astrophotography, where we use very long exposures to capture every single photon we can on nearly invisible objects, the planets are actually pretty bright by comparison, so we actually need a very short exposure time. In fact, because of the effects of the distortion of the atmosphere, we actually want to shoot as fast as possible. So fast that we might as well shoot in video. So we shoot in video. Using a super high frame rate video, we can essentially capture the very brief moments of minimal atmospheric distortion in individual video frames, thus the term lucky imaging. We will then use the best frames we get from our video footage and stack them to produce a significantly more detailed image. This is where the capture software, Firecapture, comes in. Firecapture is the software that controls the camera and has some very useful features explicitly for recording video of the planets. It has the basic camera controls you would expect: exposure time, camera gain, and your typical record and stop buttons. However, it also has an important feature that we need in order to get the highest frame rate we can get, which is called ROI, or Region of Interest. The ROI feature allows me to reduce the part of the sensor being used to just where the planet appears on the sensor, which allows the camera to achieve a much higher frame rate than shooting with the full frame of the sensor. This, combined with the high sensitivity of the chip and super fast exposure times, allows me to shoot at around 100 FPS or higher. This is why the tracking mount is important, as the mount must keep it in the frame in order for this to work. If you don't have a tracking mount, you can shoot with a full sensor and simply let it drift across the sensor, then manually adjust the scope, but using the full sensor will lower the frame rate and thus give you fewer frames to use. ROI also drastically reduces the file size. The high-speed video footage using the full 6.4 megapixel sensor for 5 minutes results in about 80 gigs of data. And now there's even more work that needs to be done, processing all the data I acquired into the final image. Depending on your affinity for navigating software, this is where astrophotography can be a real headache. For planetary imaging, I use AutoStackert, RegiStacks, and WinJupos. All of these are free, but only WinJupos is still in support. However, they each do their job pretty well, and even top planetary imagers today are still using these softwares. First, I run each video file through AutoStackert. This program essentially analyzes all the individual frames of the video file, sorts them by their quality, and then stacks them into an image. This can take a little while depending on how much data I have. If the seeing is good, it generally shows a more even quality graph, which means we can use even more of the frames I captured in stacking. I generally use between 10 to 50% of the best frames depending on how good the seeing was. Then I will take each of our image stacks and apply wavelets using RegiStacks 6. RegiStacks is a very old piece of software, but still one of the best at what it does despite no longer being supported. Without going into too much detail, wavelets are essentially using all the data from the stacked frames to sharpen the details of the image. For the first round of wavelets, I had to make sure that the wavelets applied are roughly the same, as big differences in sharpening can cause issues in the next step. After I've sharpened all of the image stacks, we will then stack these stacks to allow for even more sharpening using WinJupos. WinJupos is software designed for planetary measurement, and I assume is actually probably used mostly by planetary scientists, especially those who study the dynamic features of the likes of Jupiter. This is what the software was designed for, at least. However, WinJupos can also do image derotation. Because the planets rotate as we image them, if we image them for too long, their features begin to blur. WinJupos takes this into account, and then using the timestamps of each of our image stacks, which we take in intervals of a couple minutes each, stacks our image stacks into a final stack that sharpens some of the details even further. This really helps with the edges of the planet in particular and the inherent camera noise. I then take it back into RegiStacks one more time to sharpen it up a little bit before taking it into post-processing. I do all of my processing in GIMP, mainly because Photoshop is expensive and I've only really ever learned how to use GIMP, but it does the job well enough. For planetary images, I usually only do a little bit more sharpening and noise reduction, and then bump up the saturation and the contrast a bit to make it pop. There's some room for flexibility here as well. The colors can actually be modified a bit to match some of the more popular color schemes. For example, the Cassini versus Hubble versus the JWST. In the case of Saturn, Uranus, and Neptune, you can also retroactively add the moons if they appeared in the frame. They're usually too dim to show up normally, but if you bump up the brightness all the way and they were there in the frame, they will usually show up. Alright, that's the whole process. And if it sounded like a lot, it's because it is a lot. In the words of another astrophotographer, if it were easy, everyone would do it. And it took me a very long time to learn how to do all of this stuff. So by all means, if this is something that you would like to try for yourself, you don't actually have to do it like the way that you see me do it here in the video. There's a lot you can do with simply just your smartphone, and if you even happen to have a telescope, you can actually kind of do what I do in this video. But that's my process for planetary imaging. Hope you found this educational, possibly even entertaining. I don't know. I just felt like making this video. But anyway, thanks for watching, and I'll see you in the next one. Hey guys, thanks for watching. If you made it all the way to the end of the video, if you did, congratulations. It's a long one. But these videos do take a ton of time and effort, so I appreciate, of course, subscribing, liking, but also, of course, any financial compensation you can spare. I will leave a link to that in the description if that's something that you're interested in. Similarly, if you'd like to see more of my astrophotography, I usually post that in my Discord, so if that's something that you're interested, I'll leave a link in the description below if you'd like to join and hang out or whatever. Thanks again for watching. Bye.